this video, I'm going to go through all of the free response questions from the Princeton Review for Big Idea 4. So let's look at the first question. So in number 1, it gives you the reaction, and it says the following results were obtained in experiments designed to study the rate of the reaction above. All right, so determine the order of the reaction with respect to each of the reactants and write the rate law for the reaction. So to determine order, I'm going to look at this and see if this is going to be an easy problem or a little bit more challenging. And what I mean is, in order to determine the order for B, I need 2 experiments where the concentration of A stays the same, and I have that, 1 and 2. Same thing for determining the order of A. I need 2 trials where the concentration of B stays the same. Well, I have a couple of those, so I'm in good shape. So what I'm going to do first is I'm going to determine the order of B. So if you look at experiment 1 and 2, from 1 to 2, the concentration of A stays the same, but the concentration of B doubles. If you look at the rate of disappearance of A, that also doubles. So since the concentration of B and the rate double together, that means B is first order. I'm now going to look at experiment 2 and 3 to determine the order for A. So from 2 to 3, A doubles, the concentration of A doubles, and if you look, so does the rate. Now, keep in mind, if you don't have a calculator, to get rid of the exponents, all you need to do for the rates is multiply all of them by 10 to the third. So that for experiment 1, it becomes 3, 2 becomes 6, experiment 3 becomes 12, because 10 to the negative second times 10 to the third is 12, and the other one is 24. Okay, so do that. If you have a calculator and you're a little bit stressed out about that, then you can always just divide. So I would have divided 1.2 times 10 to the negative second by 6.0 times 10 to the negative third. So these are both first order. A is first order, B is first order, and so that is my rate law. Then it says calculate the value of the rate constant K for the reaction. So I'm going to use this rate law, and it doesn't matter which experiment I use, because remember, the only thing that can change your rate constant is temperature. Okay, so what I did is I'm going to plug in for experiment 1. So my rate is 3.0 times 10 to the negative third. I don't know my K, but I know my concentration of A and B. So I can solve for K, and I get 1.2. Now, unit-wise, overall, the order for this is second order, which means the units, molar times molar, would be molar squared. So remember, rate is molar per second. Molar squared is on the other side, which means to get rid of molar squared, I need to multiply that by molar to the negative 1, because that just makes it molar, and then seconds to the negative 1. So that's B. In C, it says if another experiment is attempted with A and B, both 0.02 molar, what would the initial rate be? So here, I don't know my rate, but now I know my K, and I know that my concentrations are going to be 0.02 for both of them. So I can plug this into my rate law. My rate equals 1.2 times 0.02 times 0.02, and I get 4.8 times 10 to the negative fourth, and my units for rate are going to be molar per second. Okay. For D, it says the following reaction mechanism was proposed for the reaction above. Show that the mechanism is consistent with the balanced reaction. So all you have to show is that A remains, B plus B is going to be 2B, so maybe circling those and drawing an arrow and showing that that becomes 2B, showing that D cancels out because it's an intermediate, and then 2C. Okay, so you can show that. It just says show. It does not say explain. So you just show how you get that and you'll get credit. For II, it says show which step in the rate determining step. Show which step is the rate determining step and explain your choice. Okay, so for here, I always like to look at my first one just to see if that works, because if my first step is my slow step or my rate determining step, then I don't have to deal with an intermediate. So if my slow step were my rate determining step, then it would be rate equals K times my concentration of A times my concentration of B, and that's what I have. So that would be my answer, and then it says explain your choice. So you need to make sure to explain it. So what I said was the rate law determined in A is consistent with the stoichiometry in step 1, making step 1 the rate determining step. So even if it's totally obvious to you, well, yeah, you have A times B in your first step, make sure that you're explaining it in terms of stoichiometry so it's clear that you know what's going on. So that was number 1. Let's look at number 2. It says the following results were obtained in experiments designed to study the rate of the reaction above. Okay? Write the rate law for the reaction. Awesome. So I'm going to see if this is going to be a tricky one or an easy one. So for determining the order of NO, I can use experiment 1 and 2 because Br2 stays the same. For determining the order of Br2, I can use experiment 1 and 3 because the concentration of NO stays the same. So this is going to be an easy one. So let's first determine the order for NO. From experiment 1 to 2, that doubles. Okay? The rate, if you look, remember, I'm going to multiply all of this by 10 to the second. So 9.6 times 10 to the negative second just becomes 9.6. 3.8 becomes 38, and then 19. So if I'm going from 9.6 to 38, I'm almost quadrupling it. So as my concentration doubles, my rate quadruples. Therefore, this is going to be second order for NO. For Br2, I'm going to use experiment 1 and 3. That doubles from 1 to 3. 9.6 to 19, that doubles as well. So Br2 is going to be first order. So there's my rate law right there. You do not need to explain how you determined your rate law unless it asks you to explain. So keep in mind the one thing I forgot in my answer. It should be rate equals K times concentration of NO squared times Br2. Okay? Then it says calculate the value of your rate constant, include units. So keep in mind you get 1 point for calculating the correct rate constant, 1 point for units. So I'm going to plug in. What I did was I just used experiment 1. So I plugged in my rate. Then I said that equals K times my concentration of NO, which is 0.02 squared, times 0.02. And what I got for my K was 12,000. Keep in mind the overall order for this reaction is third order. So that would be molar cubed. So to get rid of molar cubed, in order to get into molar per second, I'm going to multiply it by molar to the negative 2, seconds to the negative 1. Okay, so that was B. And C, it says in experiment 2, what was the concentration of NO remaining when half of the original amount of Br2 was consumed? So now we have a stoichiometry problem. Okay, I start off, I'm going to create an ice chart because it tells me I know how much I start with, I know how much I finish with, so immediately that's going to be using an ice chart. So we looked at this over the summer. I'm going to just show it to you really quickly. So initially, how much NO and Br2 did I start with? Well, in experiment 2, I started with 0.04 of NO and 0.02 of Br2. So I would put 0.04 and 0.02 for Br2. That's my initial. And I didn't put anything for NOBr because I'm not concerned about that. It doesn't ask about that. But I don't have the concentration. My change, my C in this, is going to be minus 2x because I'm going to lose NO and I'm going to lose Br2. Keep in mind the minus 2 and the minus 2x comes from the coefficient for NO. So that's minus 2x while Br2 is minus x. And it's asking when half of the original amount of Br2 was consumed. Okay? So that means in the end, I'm going to only have 0.01 of Br2 because half of it was consumed. So what that tells me, basic math tells me that x has to be 0.01. If x is 0.01, how much NO is left over? Well, it would be 0.04 minus 0.02, which would give me 0.02 molar of NO. Okay, so this concept of the ice chart is something we're going to be using extensively in Big Idea 6, which is our next big idea. Just look that through, kind of internalize that and think about what the minus 2x and minus x mean, and then move on from there. But I do want you to start to become familiar with this. In D, it says which of the following mechanisms is consistent with the rate law. Okay, so I'm going to look at my first step being slow first, just to see if that'll work, because that'll make my life a lot easier. So if you look at 2, my rate law would be rate equals the concentration of Br2, and that would be it. So unfortunately, looking at 2A, that is not my rate law, which tells me that step 1 is going to have to be my rate law. So I'm going to do this. I'm first going to write out the rate law for my slow step, which is rate equals concentration of N2O2 times my concentration of Br2. Keep in mind, because N2O2 is an intermediate, I can't leave that in my rate law. So what I'm going to have to do is set my reaction rate for NO, the forward reaction, and the reverse for the fast reaction. I'm going to set them equal to each other. So it would be K times my concentration of NO squared equals K times my concentration of N2O2 because you're in equilibrium. So what I can do with that is I can plug in K times the concentration of NO squared in for the concentration of N2O2 now. And so what I get is that my rate equals, I should have put K times the concentration of NO squared times my concentration of Br2. And the reason why I did all of that was to get rid of my intermediate. So in my explanation, because it says explain your choice, what you need to say is mechanism 1 is consistent with the rate law. Since the rate determining step includes an intermediate, you must assume that the first step is in equilibrium. By setting the rate of NO's consumption equal to that of N2O2, right, so that NO squared equals N2O2, the intermediate can be replaced by NO squared. That gives the rate law that gives the same rate law as that determined in A. So that is a great explanation. In 3, you're given a reaction, and it says it's first order for the reaction, and it gives you data below. Okay, so notice here, instead of giving you rate, it's giving you time. So don't let that freak you out. Just keep in mind we're going to be dealing with time, so probably we're going to have to use the formula, since it's first order, your ln formula that's on your cheat sheet. So for A, it says calculate the rate constant for the reaction using the values for concentration and time given in the table. Include units with your answer. So I'm going to be using the formula ln of AT equals negative KT plus ln of A naught. I get to choose where I want to start. I'm going to just start. My A naught is just going to be 0.4. That's going to be my initial. Okay, and that's what I would recommend doing, because A naught really means where you start, and that's just going to make everything easier. So I don't know my K, that is what I'm trying to determine. I know my concentration of N2O5 at all these different times. So I just chose to go from time equals 0 to time equals 20 minutes because I thought that would be the easiest thing. So it would be ln of 0.289 equals negative K times, so it actually should be 20 minutes, not 20 seconds. Sorry about that. So times 20 minutes plus ln of my original concentration, which is 0.400. And so what I end up getting here, my K would be 0.0163 minutes to the negative 1. And it's minutes to the negative 1 because my time is in terms of minutes and it's first order, so I don't need to get rid of any sort of molar or anything like that. Okay? So you get 1 point for your correct K and 1 point for your correct unit, so make sure not to exclude your units. After how many minutes will the concentration of N2O5 be equal to 0.35? Awesome, I can do this. That's my AT, my 0.35. I know my K now, I'm solving for T, and I know my A naught. So I can just plug in all of these values, solve for T, and what I get is 8.19 minutes. For C, it says what will be the concentration of N2O5? It should be N2O5, not N2O3, after 100 minutes have elapsed. So here, you're going to be calculating your AT again. You know your K, you know your T, you know your A naught, and so you're just going to be plugging in those values. Keep in mind when you solve for this, when you get whatever is on the right-hand side, that's going to be ln of AT equals whatever that is. So in this case, it was negative 2.55. To get rid of ln, you need to take E and raise it to whatever you got. So in this case, it would be E to the negative 2.55. That will give you your concentration, which is 0.078 molar, because we're talking about concentration. Okay, so that was C. Calculate the initial rate of the reaction, include units with your answer. So the initial rate is the rate at the very beginning. So I know my concentration at the beginning is 0.4. I'm trying to find rate, so I'm going to be using my rate law. So I know that rate equals K times the concentration of N2O5 because it's first order. My rate, I don't know. I know my K is 0.0163, and I know my initial concentration. So I can just calculate that, and I get 0.00652 molar per minute because the unit for time here is minutes. For E, it says what is the half-life? Well, since this is first order, I can use the equation T1 half, which is the half-life, equals 0.693 divided by K. My K is 0.0163 minutes to the negative 1, so you just divide, and what you should get is 42.5 minutes, and that's it. In number 4, if you notice, all of a sudden we've got this graph, and it looks like it's first order because it's sloped when your dependent variable, or your y-axis, is concentration, and your independent variable, or your x-axis, is time. However, you cannot automatically make that assumption. Instead, if you're not given ln or 1 over in a graph, what you should immediately do is look at the data and see if your half-life is constant no matter the concentration you start with. So specifically, what you should notice is that from 0 to 40 seconds, it halves. From 40 to 80, again, it halves. So that tells me my half-life is 40 seconds. Since my half-life is the same regardless of concentration, I know that this has to be first order. So my explanation, I would say it's first order because regardless of the concentration of the reactants, the half-life remains the same. So that would be my explanation. Not, oh, it's a curved graph and therefore it's first order. No. Look at half-life if you're trying to determine if it's first order, because you can here, because you know concentration and you know time. What would the concentration be after 120 seconds? A lot of people freak out and try plugging stuff in, but it's really way easier than that. Since I know the half-life takes 40 seconds, from 80 to 120 seconds, that's going to be another half-life, which means 0.05 molar is going to halve again, which means the concentration would be 0.025 molar. Okay, so that's AII. For BI, it says if the rate of disappearance is 2.5 times 10 to the negative third at 20 seconds, what is the rate of appearance? So remember, we can relate the rate of disappearance and appearance within a reaction. I need to use my stoichiometry. So remember, it would be negative 1/4 times the rate of pH3 equals the rate of P4, which equals 1/6 the rate of H2. Okay, so in this case, I'm going to plug in what I know. So here I know that negative 1/4 the rate of pH3 equals the rate of P4. Okay, I'm given my rate of disappearance of 2.5 times 10 to the negative third. The only thing you have to be careful with is when you plug in for the rate of pH3, it needs to be negative so that your rate of P4, which is the rate of appearance, will be positive. And what I got was 6.3 times 10 to the negative fourth molar per second. Okay, so that was BI. Then it says, how will the rate of appearance change as the reaction progresses forward? Okay, so keep in mind, as the concentration of your reactants decrease, your rate is also going to decrease because this is first order. So what I said was the rate of appearance will decrease as the concentration of the reactants decreases. And that's it. Same with the rate of disappearance. That will also decrease. Remember, they all level off. For CI, it says the experiment is repeated with the same initial concentration, but this time the temperature is set to 500. So the temperature was increased. How and why would the following values change, if at all? So the half-life. By increasing temperature, you are increasing the rate. You're increasing the rate at which this reaction proceeds. So since you're increasing the rate at which this reaction proceeds, what that tells you is that the half-life is going to decrease. And it decreases because the rate increases, meaning it's going to take less time for half of the sample to decompose, which makes sense. The faster it goes, the shorter the half-life. The rate law. By saying the rate law, what they mean is how will the order of the reaction differ? And it doesn't. The reaction is going to remain first order regardless of what happens with the temperature. And finally, the rate constant. Well, since by increasing temperature, you're increasing your rate, what that means is your rate constant is going to also increase. And it increases because if you think about it, rate equals K times your concentration. Well, my rate increases, my concentration is staying the same. So what has to happen to my rate constant? Well, that also has to increase if my rate is increasing. Okay. For number 5, it gives you this problem. Then it says the reaction above is second order with respect to A and 0 order for B. They're present in a closed container. Predict how each of the following changes will affect the rate and rate constant and explain why. So if I add more A, since I'm increasing concentration, my K is staying the same, but since I'm increasing concentration and it's second order for A, that would cause my rate to increase. So my rate will increase, but my rate constant does not because only temperature affects your rate constant. For B, you increase the concentration of B, but because it's 0 order, that will not affect your rate at all because by saying B is 0 order, you're saying B, the concentration of B has no effect on the rate. And again, no effect on the rate constant. If I increase temperature, that will increase my rate constant because my rate also increases. Now my rate increases because I'm increasing the number of collisions and I'm increasing the energy with which they collide. So as temperature increases, the rate increases because you have more collisions with more energy. And as rate increases, since my concentration stays the same, my rate constant is also going to increase. In D, I'm adding an inert gas. An inert gas has no effect on concentration. So as a result, it's not going to have any impact on your rate or your rate constant since temperature is staying the same. And finally, in E, if I decrease my volume, what effect would that have on a gas? Well, that would actually increase concentration, okay? By decreasing volume, okay, you're increasing concentration, meaning you're going to have more collisions. More collisions means a faster rate, okay? So higher concentration, meaning more collisions. By decreasing volume, a higher rate. However, your rate constant stays the same because you're not changing temperature. In 6, it gives you this diagram. Notice it asks you to justify your answer. So I didn't write these out, so you're just going to have to listen as I explain them, okay? If it didn't ask for a justification, you don't need a justification, you're fine, okay? So in A, it says the two lines in the diagram above show different reaction pathways for the same reaction. Which of the two lines has a catalyst? Well, 2 has the catalyst because the activation energy has been lowered. And that's what a catalyst does. In B, it says which of the two lines in the energy distribution diagram shows the conditions at a higher temperature. If you have a higher temperature, what that means is that the average energy will be higher. So what that means is that the second curve has a higher temperature. Notice what happens, and this is key, and we're going to come back to this. Notice that as you increase the temperature, while the average, right, where the center of that bell curve is, scoots over to the right to show it has an increased energy. Notice that its distribution, notice that it's not as tall. So what I like to tell students when they're trying to figure out what the bell curve is going to look like, imagine that string. So if I do number 2, right, and then if I decrease temperature, what that's going to do is it's going to force the energy backwards to the left. But imagine doing that with string and pushing the string on the right-hand side. That would cause the bell curve to become taller. And so that's why 1 is taller than 2. It's a great way to think about it. Which of the two lines shows the relationship of ln of the concentration of A to time for a first order reaction, okay? So your answer would be 1, and the reason why it's 1 is a first order reaction plotted with ln of concentration versus time would give you a linear slope with a negative slope, so a line with a negative slope. In D, it gives you these two, and it says which of the two graphs shows the changes in concentration over time. Well, since A is becoming B, what that means is that the concentration of A should be decreasing while the concentration of B should be increasing, so it's going to be 1 as well. Okay, so just write those explanations and you're good. In 7, it gives you this reaction. It says, what is the equation for the overall reaction? So what I would recommend is canceling out anything that's the same on both sides, and what you should end up getting is what I just wrote there. It says, identify any catalysts or intermediates. Remember, intermediates are formed and used up by the reaction. Catalysts exist at the very beginning, and they exist at the very end. So nothing that you actually cancel out is a catalyst. Instead, they are all intermediates, okay? So NH2Cl, N2H5, and OH- are all intermediates, okay? For B, it says which elementary slope is the slowest, which elementary step is the slowest, and justify your answer. If you look at the rate law there, it gives you NH3 and OCl-. Well, if you look, step 1, that is the stoichiometry, step 1. So step 1 is the slowest, it's the rate determining step, because the stoichiometry of the reaction is consistent with the rate law. That's all you have to say. For II, it says if the reaction is measured over the course of several minutes, what would the units of the constant be? Well, since it is second order overall, your units would be molar to the -1, and they told you it's over several minutes, so it would be minutes to the -1, and that's it. In 8, you've got this problem, okay? This is the crystal violet reaction that we looked at ourselves, okay? It says, what is the rate of disappearance for crystal violet from t equals 60 seconds to t equals 120 seconds? Well, I need to show the change in concentration over the change in time. So I'm going to do final concentration minus the initial over final time minus initial time. So it would be 2.6 times 10 to the negative fifth minus 3.8 times 10 to the negative fifth, and divide that by 60 seconds. And so what I get is 2 times 10 to the negative seventh molar per second. Now that should actually be negative, but since it says the rate of disappearance, the negative is implied. If the solution placed in the spectrophotometer, if the solution is placed in the spectrophotometer 30 seconds after mixing instead of immediately after mixing, how would that affect the calculated rate? Remember, as your concentration decreases, which is happening here, your rate also decreases. So if you waited 30 seconds before measuring at the very beginning, the calculated rate that you would find would be less than what it really should be, because the lower your concentration, the lower your rate. Okay, so that was AII. In B, it gives you the path length, it gives you your molar absorptivity, and it's asking what would the absorbance be. So all you're using is Beer's law here, A equals ABC. Okay, you're solving for absorbance, you know your A, you know your B, and you know your concentration at 60 seconds, which is 3.8 times 10 to the negative fifth. So your answer would be 0.99. Remember, we don't have units for absorptivity, so you're good to go. In C, it says this reaction is first order. On the provided axis, graph a function of the concentration of Cv plus versus time that will provide you with a straight line. So remember, since it's first order, that would be ln of concentration versus time, and it's going to be a line with a negative slope. Okay. In D, it says write the rate law for this reaction. Okay. I know Cv is first order, so I can ignore Cv completely and just focus on concentration of OH minus. So from experiment 1 to 2, the concentration of OH minus doubles, so does the rate. It goes from 3.60 to 7.20. So OH minus is first order as well. So my rate law would be K times my concentration of crystal violet times my concentration of OH minus. It asked me to determine my rate constant. I'm going to use experiment 1 because why not? So my rate is 3.60 times 10 to the negative 7th. I've got my two different concentrations there. I solve for my K, my rate constant, and get 0.055. It's second order overall, which means the units are going to be molar to the negative 1, seconds to the negative 1. Finally, it says determine the initial rate of formation in experiment 3. So all I have to do is plug in my value. So I know my rate equals my rate constant, 0.055, times my concentration of Cv plus, times my concentration of OH minus. I solve for my rate, and it's 4.1 times 10 to the negative 7th, and my units are molar per second, and that is it.